what we did was we learned that there is something called SVM, and this SVM has two parts. One is the algorithm that does the optimization and finding part, right? And second part is the objective function, right? Or you can say the cost function. And the cost function that we saw was a little different from regression. In regression, we were trying to figure out the line that, right, that was basically fitting through the data and so on. And in here, in a classification, what we were doing is we were trying to come up with a line that separates them really well. Okay, so in case of regression, we had used logistic regression kind of objective function whereby we create our expression mathematically such that a decimal prediction could be converted into yes or no and so on, right? So in case of SVM, the one thing that we learned was if you go for classification, we'll talk about regression very soon. So in here, we learned was that we try to create this big lane as big as possible. And for that big lane, we will have a mathematical expression. And using the gradient descent or stochastic gradient descent or batch gradient descent, we will optimize that formula of maximizing the width. While SVM does a very interesting thing, right? SVM also has something an algorithm, just like we had that normal equation whereby we differentiated and equated to 0, unlike gradient descent, because gradient descent was iterative algorithm. Similarly, this SVM has a very clever algorithm which does the job at very quickly, basically like the way we do in geometry, that we try to find the maximum length of things using geometry and calculus. That's what has been done in SVM, that pick up 2 points, try to figure out the maximum distance between the 2 points using geometrical constructs and calculus, just like normal equation. That's what is the SVM. So in gradient descent, we try to move towards the side where rate of change of gradient descent is 0, right? No, sorry, rate of change of error is 0. That's what we try to go to, because that's the point where error will not go up, right? So we try to go to that point where the rate of change of error is 0, right? So gradient descent helps us by iterative way, while the normal equation, we just take the rate of change of error and make it 0 and calculate backwards the various model parameters, right? Yes, for there, we only need to do matrix inverse. Thank you, Deepak. Matrix inverse takes a little bit calculation, because you remember when we solve two linear equations, right? Ax plus by equals to something and cx plus dy equals something. When we try to solve them, it takes a bit of hard work. And if these equations become like 3, 4, 5, or 6, it takes a little bit, time to do that. And that's what is matrix inverse. And that's the only calculation we were doing. We're not iterating there. We were basically just solving these parallel equations, which you got after partial differentiation of the error, equating rate of change of error to 0. Rate of change of error with respect to each of the thetas, we made it 0, calculated all thetas, that's what was it. Similarly here in SVM, what we are going to do is we're going to maximize the lane between the data points, and for that, whatever is required is done as part of SVM. Now, I'm going to move ahead now. So great. So we learned was that in case of SVM, we are trying to fit a straight line into the data, or we are trying to fit a straight linear street between the data, but that's not going to solve problems where the data is like this, where the data is nonlinear. And how did we generate nonlinear data? One was using y equals x square kind of formula. The other one we generated based on a function provided by scikit-learn called makeMoons. MakeMoons basically has two moons, into each other. And we learned that if we introduce the polynomial features, then our SVM can fit many kind of streets between each of the two features in all kinds of dimensions. It can fit the straight streets, and those ones, when we present it in the normal one after classification, it actually comes out as a boundary which is not linear, right? So this way, basically, by introducing features, we are able to solve even nonlinear. Okay. Question from Gonzalo is that under nonlinear SVM, there are multiple support vectors, streets, etc. That's right. That's right. You can think of that under the hood, the support vectors, there are multiple support vectors that have been created, and the combination of those is nonlinear. All right. So here, when the decision function has come, the decision function would be having, you remember we talked about OVO, right? OVO. Similar to that, the since we have many features, the street has been generated for between every two combinations under the hood, and so on. Question from Gonzalo is that are there the violation the same across all the streets? Are the number of violations the same across all the streets? Good question. Good. So imagine this, the way we explained earlier here. Let's go back here, right? Here, right? So what we did was we created, earlier there was only X1 feature. We created X2 feature, and we drew a relationship between the two, right? And we came up with this, right? And so now you can see that this one doesn't make sense, in our real case scenario, right? Now we will actually like to plot it. We'll actually like to plot it just against X1, right? When we plot it against X1, what will happen is we'll say that, okay, we'll plot these values as such, and we will basically mark the decision boundaries based on the results. Okay, when we do just between X1, right? So we'll say, okay, for this, it is blue, so we draw a line. Then for this, it is again blue, then we'll draw a line. And then for this, it's green, so we draw a line. And so this way, we basically, if you go back here, and let's say here, when we draw the decision boundary as in the one that is being generated by these new parameters, it'll be, our decision boundary will be like this. Our decision boundary will be like this. Okay, and that's quite interesting, because this way we are able to separate them. Okay, so the violations will be different in different street. That's a good point. So yes, so see, in case of this, when we are generating this kind of model, it's going to, the violations will be, so question is, let's say, okay. The challenge which you are finding here is that the street that we are going to draw probably is between this and this, this and this, this and this, this and this, and therefore there will be multiple streets, and I'm just wondering that, do we need to draw so many streets, or geometrically we can fit everything into one? As per my understanding of the maths of SVM, you'll be basically drawing that we will be basically for every two pairs of the features, we will be doing that. Okay, specifically the OV, it's kind of OVO. Okay, not on the label, but on the features. All right. So here we will be basically picking up two features and try to come up with a boundary. And when we bring together all the boundaries into a single boundary, then the boundary comes like this. Okay. So number of violations will be different across different streets. Good questions. Very good questions. All right. So now we have to. Okay, so let me go to my home drive. You might have to pull the new data from the repository. Okay, so you have to pull the data from repository, and so I'm going to go to CDML, CD machine learning, and here you have to pull the new versions of notebook from the repository. Since I have a lot of work here, right, so many things, I'm going to just keep a copy of it, and then, okay, I'm just going to keep a copy of my ML repository. Okay, so I'm just keeping. All right, I hope I have that much space. I'm just keeping a copy of ML copy so that when I pull a new version, it should remain there. Okay, I'll do the reconciliation later, like these are the changes I made and these are the changes in the repository. I'll do those reconciliations later. And comparing these notebooks is becoming difficult for me when I'm trying to compare that these are two reports. The whole thing get lost in that XML, not XML. It's a JSON. All right, maybe what I'll do is whatever is taking too much time, du minus csh. This is a quick way to find the sizes, and you can further do sort minus h. So okay, so you can see that this one seems to take a lot of space. Okay, so looks like, all right, so I'll just try to see if I can delete some part of it. Okay, just do a ggib so that it doesn't become. All right, our cvf and ml copy zip. I'm just keeping it separate. I'll let it be for now. Okay. All right, never mind. So let's go ahead and, okay, so there's a lot of junk that has gathered in my home drive. I'll do clean up probably later. Okay, because it has been pending for some time. Now moving ahead. So here we have ML, and this is the one that we want to update. So we pulled a new version. It says that there are local changes in your files, and would and the following files would be overwritten by the merge. Okay, so I'll just say git checkout. Okay, I can say git checkout, and that's it. Okay, now I can quickly say pull again, right? So now it has updated. So what you can do is you can go to ML folder if you don't want to keep your changes. You can simply say git checkout. A question from Deepak is, what if we use fetch instead of pull? Fetch is basically to bringing all the branches. Okay. But it doesn't do any harm. Good point. Good point. Okay, so you can say git checkout and git pull, and there you are. All right. So is everybody able to get the newer version? Let me just give it a shot. If it is working or not, or did we mess up something? Okay, is it killed? Okay, now it's running, opening up, and here we go. Where is the support vector machine? All right, so we're going to run it till there, and then we will. A question from Deepak is, because I don't want to overwrite my changes, just want this particular file. So just check out that particular file from master. Yeah, that also is a cool idea. So what you can do is you can just get that file, all right, and that's all. Okay, yesterday's changes, I want to keep them. Okay, that's why I had copied it. Right, or you can just simply say git checkout and the file name. No, but what's happening here is this, that we are git checkout is checking out from local git repository to my current project, right? Then git pull brought the data from the server. Okay, git pull got aborted because there were local uncommitted changes were there, right? Therefore, it got aborted, that you may end up messing up with your data. Therefore, first either commit it or abandon it. Okay, so that's why what I did was I did git checkout. It cleaned up. Checkout means actually it cleans up your entire changes. So be careful with checkout. Checkout will, whatever un, uncommitted changes there, those will be washed out. Okay, with checkout. So keep that in mind. And git pull, and then we are good to go. And again, I did git checkout, and now since we are at the fresh state, git pull and git checkout will not result in anything. Okay, git pull, I hope everybody's clear. Git pull brings the changes from the server, right? Git like origin, and git checkout from the local repository to this. So there are two repositories, one on the server and other is local, and git pull basically does bring the repository from remote to the local. Okay, so try that out. Now, all right, this is where we are. I'll just keep running from here and that'll be easy. So I'll just keep pressing shift enter, shift enter, shift enter, shift enter, shift enter. Okay, so far so good. Moving ahead. Good. Okay, so this is what we understood till yesterday. Okay. All right. So now we talked about the polynomial features, and so polynomial kernel, adding polynomial features works great. Low polynomial degree cannot deal with complex data sets. High polynomial degree makes the model slow due to huge number of features. How to overcome the slowness due to huge number of features? There is something called polynomial kernels or kernel trick. All right. So basically, when you have the polynomial features, the one that we did just now, we basically added all kinds of polynomial degrees into our data set, right? So when we are using the polynomial features, the low polynomial degree cannot deal with complex data sets. Like if you have really intermingled data set, and if you're using x square or so, it doesn't solve it. Okay. High polynomial degrees make the model slow due to huge number of features. Okay. So high polynomial degrees, as in the when we are having like 10 or 20, if you see here, we had example and discussion here somewhere. So if you have two features already and you say polynomial degree of 50, it becomes 50 C2, I think. No, 50 C0 plus 50 C1, 50 C2, like that. Okay, and that takes a lot of time. Will be like feature explosion. There are like hundreds and hundreds of features, even for a very low degree. Okay, therefore, the slowness due to huge features will happen, and to solve that, we use the polynomial kernels or kernel trick. Okay, it makes it possible to get the same result as when using the high polynomial degree without having to add features, which makes the model slow. Okay, so it makes it okay. So what we do is we will add these clever features. We'll add these clever features, and those clever features are we call them kernels or kernel tricks. Okay, so these clever features makes it possible to get the same result as using the high polynomial degree without having to add the features which make the model slow. So kernel trick is one such game whereby we come up with these one or two clever features which basically make it possible to handle the nonlinearity. Okay, so so it can be implemented in scikit-learn using SVC classifier without having to use polynomial features as linear SVC. And here a simple example would be that we are using pipeline, and there is a scalar, standard scalar. This is normal thing, and afterwards, instead of using the linear SVC, we are saying SVC. And upfront, we are telling that the kernel is polynomial, and this is the degree, and this is the coefficient. Okay, and SVM has those this inbuilt, so it trains SVM classifier using 10th degree of a polynomial, and so on. So here we said kernel as poly and degree is 10. So basically, without having that much overburden of so many polynomial features, SVM was able to do it really fast. Okay, and now here you can see that when these are the hyperparameters, like there are three hyperparameters: degree, coefficient, and C. Okay, C is regularization parameter. Degree, there is R. Let me go back. R is that coefficient actually. Okay, so there are these three hyperparameters, and basically when we are mentioning polynomial kernel, there is some kind of magic that SVM is doing, where we are given these three knobs that we can control. Okay, so here we are, you can see that the C, the regulation parameter we are keeping same, and so on. So by controlling these three parameters, when you can see when the degree is 10, you can see the degree is 3 here, degree is 10 here. what's happening in this case is that we are degree is 10, degree is 3. So it's not that regularizing, it's not taking into consideration more data points. And here it's taking in consideration these more data points. Okay, so let me just try to show you here. All right. Okay. Okay, let me see if I could do compare without the coefficient as 100. I'm just going to keep the same coefficient in both the cases. Okay, this is both have R as 1, this one also R as 1, C as 1, and this one has degree as 10, this one has degree as 3. Okay, let's change the label. Okay, now let's take a look at this, what's going on here. So for when we are changing the degree, these are basically kernel tricks. So the we are asking SVM that do the kernel trick, meaning internally create something like equivalent of creating so many features. Instead of creating so many features, it's doing that mathematical magic of adding so many features without really doing that. Okay, so that's basically, you see here that here degree is 3, degree is 10, and this degree as 3 has this kind of behavior, while degree as 10, you can see that it's more overfitting. This is more overfitting, right? Here, and maybe I could compare it with this. Okay. All right, let me just see if I could paste that image here. So this was with the linear SVC. This was linear SVC. This was with the kernel trick with degree as 3, kernel trick as degree as 10. Now, yeah. So this one was with so many polynomial features. This one was using kernel trick. So you can see that it's actually pretty good. Okay. Though when we are increasing the degree, what's happening is it's going closer to the side where there are more data points, right? It's touching them instead of going between them. You remember the way we had planned earlier that it should be kind of having the best margin. Here it is having a good margin from the data points. All right, this is how you can experiment with these values the way I have shown you. Just try experimenting with these coefficients, degrees, and so on. Try putting the degree as 10 in both the cases, and just change only the coefficient. That will give you a clear idea. So I'm just changing the coefficient only this time. Okay, so this time degree in both the cases is 10. Okay, but we have changed R. When as we increase R, it basically looks like this. Do you see any difference? Okay, so it has ignored, in this case, it has ignored this data point, while in this case, it has not. So even when the data is not there much, it tries to kind of touch them. So, okay, so R looks like a regularization parameter. Yes, and okay, so try experimenting with these three hyperparameters, but there's no straight way to find them out. We can only, express their values right now in words, but the true understanding of these will happen when you do the hyperparameter optimization. Okay. Question from Deepak is kernel available in logistic regression of linear regression class or only SVM? Only SVM. Okay. There the kernel's meaning has been, kernel has been used in many, many more words. Sometimes we used to call, earlier the kernel was, even models we used to call it kernel sometimes. And the kernel has been overly abused term. And the SVM kernel here essentially is, it's a internally, the way you can infer it is that it's basically adding features, okay, to solve the nonlinear problems without really adding more and more columns. So it's kind of a mathematical trick to do that. Okay, so what we yes, so we can use this as a general concept in the other polynomials. That's right. Now, whenever we see our data as nonlinear, we generally used SVC, kernel as poly, and so on. Okay, so this does a pretty good job. And so instead of using linear SVC or linear SVC, we are using SVC here. Earlier, we had added the polynomial features. Here, we are telling the SVC itself to do that polynomial kernel internally. So this SVC with kernel as poly is faster than linear SVC after adding the polynomial features. That's the crux of it. Okay, so you just compare it and you'll get an idea. Now, there are some more ideas that people used to do very often before the neural networks came into play. And those ideas were like adding the features. Just like we added the feature in case of end-to-end project, whereby we divided the two things and put them as one column, right? What were those two things? The bedroom per room, right? Bedroom per living room or bedroom per room. Those kind of couple of features we had added, right? Similarly, what we used to do, and we do even in today, those who are using SVM, right? So what we do is we basically introduce some more nonlinear features, okay? And these features are called similarity functions. Similarity functions measure how each instance resembles a particular landmark. Okay, let's say you have a column. You have a column, and these columns, this column has some linearly increasing value or so. And when you observe the outcome, based on this input value, sometimes it becomes difficult. Sometimes it becomes difficult to to um, to differentiate. Okay, taking the same example as this one, right? Here, this one, right? So what was happening is here, what was happening is that the outcome was rectangle here, and then triangle, then rectangle. So though the value of x has been changing, the value suddenly appears here. So what we come up with, a different set of features, what we came up with, a different set of features, x2, right? Whereby here we just squared x1, right? So instead of that, what we do is we come up with something like how far is each data point away from the middle point, okay? Like this one will be two. This first data point will be, this first data point will be very highly away from the center, then so on, and then increasing. So we come up with this kind of features whereby we introduce the feature which is extremely non-linear, and that helps us number of times to come up with better results. Okay, let me just move ahead again. I'll just describe it again. Yeah. Okay. Yes. Oh, this is the example we had already put in there. I did not need to go back. Okay. So, question is this linearly separable? Answer is no, right? Can we separate that? Okay. Let's say there's only one column x1 on the basis of which we are saying whether this is rectangle or square, right? Now, so if we come up with something called landmarks, okay, let's say this central data point is the landmark, this is the landmark, and we measure how far are these points from the landmark, and we come up with that similarity, or how similar are these data points to this landmark. Okay, what will happen is if you draw those landmarks, what will happen is the similarity features like x2, right? If based on one landmark, the distance or similarity goes up, then goes down. On this landmark, the similarity goes like this. So you can see that if you choose different landmarks, it'll be different. Okay, let me again explain what it means. So there is something called the distance formula. Okay, and the distance formula is essentially calculating distance. Okay, calculating distance. Now how it's calculating the distance or similarity, let me just say similarity. This, let's say this is your milestone, or this is your landmark. Okay, this is your landmark. Now landmark is very similar to each other itself, therefore the similarity is 1. This is little away from it, so its similarity is little low. This point and this point are both away equally from the landmark, therefore both the values are 0.75, 0.75. Then this particular landmark is here, so it is around zero point 0.2, zero point 0.3 probably, zero point 0.3 here. You can see 0.3 probably here. And in the similar way, this is also going to be 0.3 similar. So what we did was we calculated a kind of similarity with respect to the distance, or you can say the distance from the data point. And that came out as like this. Instead of keeping it straight, linear, right? We're using this kind of formula whereby we are first calculating the distance between x minus L, okay, and then squaring it. Gamma is our hyperparameter, which we can tweak it in order to do something, right? So what we did was we computed the distance and did the exponent. So tiny distance leads to huge value, okay, because of its being exponent and so on. Now since distance was 0, so e to the power 0 is 1, and when the distance was something, that distance then we are doing square of it, therefore it comes out like this. Okay, so we could actually simply do x minus L as well, x minus L square as well. That could also give us this kind of curve, but we wanted to emphasize it more, therefore we put e to the power that is square of the distance. Okay, double pipe means the L2. Remember that Cartesian distance. Okay, so is that. So it's essentially, since this x is a vector, these are all the list of values. So for each of the list of values have been subtracted from one particular data point, and from there, or L means landmark. This is the landmark which we have chosen, and what we've done is subtract landmark from each of the values and square it. Okay, so the answer of this one is going to be a list of values or a vector having this new feature. If we took the landmark as x3, if we took the landmark as x3 here, then the curve that will come out will be like that. Okay, gamma is just, we came up with the number, like let's just multiply things with gamma and minus gamma actually, so that this value e to the power something doesn't become in millions, it remains within 0 and 1. So gamma remains as another hyperparameter, which we can further tune it. Okay, so we can, with gamma, we can increase the emphasis or decrease the emphasis. All right, so if we take the, now question always remains that who will be the landmark? Should we take x2 as landmark or x3 as landmark or so? Okay, so this is where the feature distance or the similarity we have put down comes into play. So if we basically, let's say there was, okay, so if we do the, if we plot after creating the classification here, so let's say these were our data points, these were our data points. They will, after introducing the nonlinear features, things are going to look like that. Okay, so all right, so basically using scikit-learn, we can define similarity function to be Gaussian radial basis function, which is equals to 0 far away to 1, which is at the landmark. Okay, so we can simply define our own function. Okay, we call that radial basis function, RBF, and we call it Gaussian. This is how we computed e to the power minus gamma multiplied by the L2 norm of the x minus landmark. So whatever landmark you give, whatever data point you give, it'll return you the new value, right? And this is how it looks like. We talked about it. And we can observe the differences here after changing the values. Okay, so now the same data which was at 0, 1, 2, 3, it looks very much manageable. Okay, let me just show you here. What happened here? Yeah, we are here. So we defined it here, we defined here. Then, okay. Okay, this is where we are. There's nothing much here. So we have created Gaussian RBF. So given a landmark, given the data, it and given some gamma value, it gives out the resulting list of new features, new feature values, right? Okay, and that's about it. So we can use this Gaussian, we can simply use the RBF by saying, instead of saying kernel equals poly, we could simply say kernel equals RBF, and that's pretty much. All right, that's all we need to do, and let's take a look. So if the gamma is 0.1, this is how it looks like. Meaning gamma is 0.1, that means that the line that we have is very straight. If the gamma is 5 and the C remains same, this is how it looks like. If gamma is 0.1 and we put C as 1000, that means, meaning we increase C, okay? Okay, and then we get this kind of boundary. And if we, right, for this kind of gamma S5 with the new feature, with the new RBF function, we are getting something like this. It's extremely nonlinear boundary. You can see this is how it looks like. All right. So you can see that with by tuning gamma and C, we are able to really solve nonlinear problems. We are able to solve nonlinear problems. All right. So what it's a pretty simple thing that we basically came up with this technique of generating the distance, generating a new feature based on the kind of distance from the some landmark. A question that people generally ask is that how to select landmarks. One is that we can create landmarks based on each of the instance of the data set. Now that becomes disastrous, meaning for every instance there will be one feature. If there are 10,000 instances, then there will be 10,000 features added. Okay. So it's going to, that's a downside. So if your data is if your data has so many instances, then it will add so many columns. Like for example here, how many features should be added to this in order to get the results in case of RBF? In case of RBF, what will happen is if we are taking every value as a landmark, then we will be computing those many new features. Okay. Since there are 9 data points here, there will be 9 new features added to it. So question is ideally how many features should be added to this 9? The training set converts the 9 instances to 9 features. Imagine doing this with a huge training data sets. Okay. So when we are adding RBF kernel, it becomes extremely slow with higher degrees. Now, the polynomial features, when we are adding polynomial features, it becomes slow because we have so many features. Similarity functions become slow with higher number of training data sets. And SVM kernel trick solves that again. Okay. Now, in case of RBF, we can control how many features should be added. Therefore, we can just if we're using RBF, it lets us to get similar results if we had added many similarity features without actually having to add them. Okay, so you can try you can try giving the doing the RBF kernel part. So all right, let me go back what we were talking about. Normally when we are adding polynomial features, it becomes very slow. But SVM allows us, this mathematical way of doing it, allows us to do the same magic of adding polynomial features without really having to add them. Similarly, the RBF, if we are adding more RBF features, then normally what happens is that when we are adding RBF features, the number of RBF features that are going to be added will be based on the landmark from each instance, and that would lead to huge number of features. And therefore, the RBF normal kernels are not really appreciated. But SVM RBF kernel does the same thing without really adding the RBF features. So it does the magic, mathematical magic of getting the same results as adding so many features. All right. So here we were trying to show you the different kinds of different impacts of various hyperparameters. So A question from Deepak is, which plot is the right one amongst these? The gamma as zero point 0.1 and C as 1000, right? So gamma is the impact of gamma signifies the impact of the new features, right? If the gamma is more, the nonlinearity is going to be more, right? Here the gamma is zero point 0.1, that means it's kind of not much of an impact. There's not much of a kernel over here. There's not much of a kernel, therefore it's trying to draw the straight line, right? But the moment we start increasing gamma, we are kind of increasing the similarity functions, right? We are increasing the RBF, the impact of RBF, therefore it starts to come up with this, okay? Now, in the similar way, if we also increase C, keeping the gamma as same, what happens is it further comes up with more nonlinearity, see? And so if we increase both gamma and C, you can see that it tries to kind of fit almost everything, right? Almost everything, and this is a good model to have, okay? But you can also see that between this and this is probably the best out of all of the moon, all of the things, because this one is closer to the moon, okay? That basically there were two moons supposed to be there, and since it has figured out the boundary for one moon, you can always figure out the second moon, okay? All right, so this is like moon, but this also is considered really well, because imagine that there is a data point here. Imagine there is a data point here that will be classified as the other moon, not this moon, okay? So out of these, in my opinion, this model, or this model seems to be good, okay? And yes, because if there's a data point just here, will be classified as this. While in this case, if the data point is just here, it would not be classified as this. Okay. A question from Robert is, what would overfitting looks like? What would overfitting? Good question. Good question. Overfitting looks like when we don't want to leave anything. This is actually how should I say? This is actually an example of overfitting. If you see so many boundaries, it's actually trying to overfit. All right, this is definitely underfitting. Now, out of these, and these, right? This is also sort of overfitting, because for the unseen instances, yeah, for the unseen instances, it's not going to work so well. Okay, so this one is definitely overfitting. Okay, if you put a data point here, though it belongs to this one, it'll be classified as this one, right? If you put just the data point here, okay. And Gonzalo's question is, how do you know it is the best? Are you supposed to run the test data? Yes, that's correct. So we are supposed to run the test data and then come up with who is the best, okay? And try to see if basically for unseen data, the data that it has not seen, until we test it on that, we won't be knowing whether it's overfitting or not. Okay. So again, the story goes back to the grid search, that we do a grid search on gamma and C and figure out what are those parameters, those values of gamma and C, which give us the best results on the test. Okay. A question from Deepak is, so C is to regularize in case overfits? Yes. C helps us in regularization. So will increasing gamma will overfit, and increasing C will regularize it. Yes, that's right. Very good questions. Very good questions. So, and this is a very important question. So, C will regularize. Yes, increasing C will regularize it. We'll try to force it. And in case overfits, after seeing the test data, I mean running on test data. Yeah, that's right. So we will tweak C in case test data shows overfitting. That's right. Okay, try experimenting with both the gamma and C's, and probably try using the grid search or cross validation to test it out on basically various parameters. Okay. Okay, so increasing gamma makes bell curve narrower. Increasing gamma makes the bell curve narrower. Yes, and and the opposite is also true. So decreasing gamma makes the bell curve wider. Reduces increasing gamma reduces the influence of each instance. Reduces increasing gamma reduces the influence of each instance, meaning okay. Let me turn off my phone. All right. So increasing gamma reduces the influence of each instance. Decision boundary becomes irregular, and so on. Okay. All right. So there are a couple of things we learned, and a question from Deepak is which one we prefer, polynomial kernel or RBF kernel? Which one we prefer, kernel is polynomial or RBF? All right. So kernel as poly or RBF. So we prefer actually the kernel as a RBF because kernel as RBF does a very good job. And yeah, generally our preference is RBF, and but there's no harm in also just taking a look at the kernel as poly. All right. And a question is that which kernel to use when? So thumb rule is we try linear kernel first. Linear SVC is faster than SVC kernel equals linear. Okay. And without polynomial features, this one is generally faster for larger data set with a lot of features. And this is one thing. And there's a little bit of more implementation related things. So first of all, we give a try to linear kernel first, then we do Gaussian RBF kernel, and for other things like polynomial and so on, we do the cross-validation grid search, and that helps us either in fine-tuning the the parameters or figuring out better kernel. Okay, so because the way we came up with RBF, there are quite a few ways of kernel that has come up. So the linear SVC is based on a library called liblinear. It scales linearly with number of instances and number of features. It does not support any kind of kernel tricks. And the time complexity of linear SVC is O m into n. If there are m instances and there are n number of columns, the time it takes is O m into n. Now, if you have a million features, and if you have a million rows, then this may not work so well. Okay, so as a thumb rule, the general idea is to use the linear SVC when there are small instances and a small fixed number of features. Okay, in those cases, like small number of features, in those cases, we use linear SVC. Now, the SVC class that is there, there is, other than linear SVC, there is something called SVC class. It is based on, instead of liblinear, it is based on libsvm library in C. And this is basically the actual SVC. This is the actual SVM, which supports the kernel tricks. The time complexity is either, it varies between m square into n to m cube into n. It becomes really slow when the number of training sets, number of instances in the training set increases. It's perfect for complex but small to medium training sets. Okay, so if you have smaller data, as I was talking yesterday, that let's say you are trying to do face detection in your company, and there are maybe 100 to 200 examples. In those cases, what people generally do is, first, they will convert the face into the features by the way of FaceNet, which is basically converting each face into, say, set of 100 values or a vector of 100 values. And once you have each face represented as 100 columns, right, then you can use SVC class. Okay, because you have 100 columns, and if your team has, let's say, 100 people in the team, and you want to just, whenever they enter your office, you want to call out their name. In those cases, you could just use the SVC classification, and it'll be pretty simple. Okay, it'll be pretty simple, and that's where generally SVMs are used. So in the pipeline, first you're using FaceNet, which is a pre-trained neural network, which knows how to represent the faces, which has been developed based on if two faces are very similar, their vector differences will be very small. Meaning, if there is one face whose 100 photos have been taken at various times and from various angles, their vector difference is going to be very small. So that vector, converting that image into a vector, such that if the face is same, the vector difference is going to be very tiny. And that's how the face embedding, or FaceNet, or we or what do you call that, feature extraction of the face has been developed. We'll be talking about how to build the feature extraction yourself in the neural network. But for now, know that SVMs are used very often when the data is very small, but you have huge non-linearity and very difficult kind of data, because the neural networks are great when it comes to humongous data. If you have huge data and you want to train and you want to get the results, or you can say that in case your problem statement is extremely nonlinear, such as self-driving cars and faces and the videos, the the neural networks seem to do a great job, but that requires huge amount of training. Okay, and therefore when you don't have a lot of training data, neural networks may not do a great job. Okay, and that's where these techniques like kernel, techniques like SVM come into play. So generally, the important part is that it's good that we brought it up, that when you are using, say, I'll just show you FaceNet. Okay, so take a look at FaceNet here. Okay, classifier training, and people must have done SVM. Okay, so let me just see again. Google FaceNet. Have they taken offline or what? Okay, so this is a common technique that people use. Okay, so again, let me just draw it, and I think I can take a look at it later. Is it that particular example I'm not able to find right now? Looks like they have taken it offline. So, okay. So what's happening is that there is the face of somebody, right? And it doesn't look like face. All right. Let me see if I can draw. Okay. Okay. So you can see that I can draw really horrible faces. Now, when you pass it through a FaceNet neural network, so what it converts it into a list of numbers. Okay, these are the list of numbers. Okay, so let's say 100 numbers. All right. Now, a good part about this FaceNet, the way it converts these into numbers, the way it converts this into numbers, that if let's say this is vector v1, which is my photo today, and vector v2 representing my photo tomorrow, so v1 minus v2, either L1 or L2, will be really tiny. Okay, meaning the vector differences between the two face embedding generated by FaceNet will be such that, because this is how the neural network was trained. For neural network to be trained, the purpose was come up with those vectors, come up with the vector for the image such that same person's two image should have very tiny difference. Okay, now, so what it leads to is this vector starts representing the face, and same thing we do with the words, with the sentences, and with the words in the language, that we convert each word into features, and then we can apply the normal classic machine learning. Now on this, if you want to tag it, let this is Sandeep Giri, and let's say there is another person who's embedding, we know that it's Sumit. Okay, and we train SVM on this because we don't have too much time taking Sandeep's photo or Sumit's photo or Satyajit's photo, too many photos. We just take 5 each photo of everybody. We take 5 photo of each of the person from different angles, and we basically come up with the SVM classifier here, that this vector represents Sandeep Giri, this vector represents Sumit, and using SVM, given a photo, whenever somebody is walking in, what you do is you ask FaceNet to convert that person's photo quickly into embedding like this embedding, and then you ask SVC to convert that into a person. Okay, so first translation is using the FaceNet, and then your SVM model. Okay, and that will give you that this person is Deepak, Gonzalo, Jay, or Nikita, like that. So you should give it a try in your free time. This is going to be quite much fun. It's going to be quite fun to do this, and important part is that all of these pre-trained models are available today. You don't need to really do all of this. You only need to focus on your SVM part. Okay, is it clear to everybody? Yes, you should give it a try. Okay, and so the point again I'm trying to make is that though most of the work, most of complex work has shifted to neural networks, but a lot of things wherever we don't have too much of data, a lot of things we still do in these models, either using recent trees, using the linear regression, or maybe SVM. That's why we have not entirely deleted this chapter, and we're going through the entire one. But we are not going into exact algorithm, what's going underneath. We are leaving it aside. I'll just give you the reference. If you are interested to learn how exactly SVM is working, I'll give you the link. You can go to that one, right? Because that particular website, the owner has done a very good job. Okay, so important part is with SVC, it becomes slow when you have just too many instances, and therefore we use linear SVC, SGD. We use the SVC when you have small number of instances. A question from Deepak is, so all the deep learning techniques need huge data? Yes, so the most of these techniques requires a lot of data, a lot of instances, and specifically extremely nonlinear ones. like the visual, the video, the self-driving, like all of these requires really good amount of data. Okay, or you can say that when you have good amount of data and you would like to come up with better results, then you generally go with deep learning techniques. But but if you have a small amount of data and you want good enough results, you might go for SVC or listen. All right. So the linear SVC is fast, SVC is slow for large data set, perfect for small but complex ones, and so on. Okay. All right. So that was a quick overview of SVM classification. Let's get started with SVM regression. SVM regression is again two parts: linear SVM and linear SVR, and with epsilon and so on. So we will just take a look at the various classes that are available, and we will basically just go through the basic concepts. We were starting to discuss how we can convert our the theory of fitting the widest possible street that we used for classification. Can we do that same thing for regression? All right. So in case of SVM classifier, what we were trying to do was we were we find the largest possible street between the two classes such that there is a such that we minimize the number of margin violations. Okay. So what is that largest possible street between two classes to minimize the margin violations, right? But in case of regression, what we do is we fit as many as instances possible on the street while limiting the margin violation. Okay, so we come up with a street which can fit, which can fit the maximum number of instances within the street. Okay, which can fit into that, and the middle line of that street is our model. Okay, now if we have a really big street, the chances are that we will be overfitting, and will be basically, if we try to go through every data point, we'll be overfitting. Therefore, we have to keep this street as narrow as possible. Okay, as narrow as possible. And in case of classifier, we want to keep the street as wide as possible. All right. So the width of SVM regression model is controlled by hyperparameter epsilon. Adding training instances within the margin affect does not affect the model's prediction. Hence, the model is set to be epsilon sensitive. Okay, just like we had C in case of SVC, here we have epsilon for SVM. Here we have epsilon for SVR, not SVC. And just like we used linear SVC, here we use linear SVR. Okay, so you can use any epsilon, maybe 1.5, or even if don't use it, it'll assume some epsilon by itself. And all you need to do is say SVM regression dot fit. That's all. And linear SVM regression is scikit-learn. Let's say generating random numbers and making relationship. Let's say we come up with a very simple line. Okay, y equals 4 plus 3x, and we are generating this line by adding a little bit random number on both sides. This one is entirely randomly generated data. Here we are adding a random factor just to make it a little more simpler. Now we are saying plot.scatter, right? So here, okay. All right, so we are basically trying to plot it and then show. Okay, so this is how Revel basically makes it a single um, row of values. Okay, it makes it a single row of values instead of having instead of it having it being two dimensional, it becomes single dimensional. Here in case of this, it's basically one column and m rows, right? X is basically one column and m rows, right? Here it's basically till this point of time before we do revel, this thing is going to be m rows and one column, therefore we are doing revel so that it becomes simply a single dimensional array of values. Here is two-dimensional array of values. It has the m by n. Good, good question. So yes, I hope everybody is with me. And right, so generating random numbers and making a relationship, that's what we were doing. We generated y, we generated x, and for each, the y is generated based on x. So this looks like a little more, very much, spread out. Okay, and in reality the data is most likely like this. Now what should we fit into this? That's what we want to figure out. Let's say we want to fit a straight line, then there'll be some straight line in this such that the overall error should be minimum, and this should not capture the, we know for sure that it's basically a straight line with the noise. Okay, somebody should not come up and say that this is a curve like this. Okay, and all right, so basically, all right, now here we're fitting a linear SVR model to the data, and okay, so it's pretty straightforward. All we need to do is we initialize linear SVR, then we do the fit, then we are basically generating the linear space from 0 to 100, and then we are, yeah, from this model, we are figuring out the coefficients, right? This is the coefficients, and this is x1s, plus here is the intercept. So this is how we are figuring out y's, and then we are plotting, and so on. So this is how it looks like. So from the model, we figure out the intercepts, we figure out the coefficients, and the way we convert the slope, we find out the slope is by multiplying the coefficients with x's. Okay? No, actually this coefficient means slope. So we find out the slope, we multiply it with y. So it's like y equals m into x plus c. Okay? So this is how the y looks like. And so then we also have something called epsilon. Epsilon is the width of the lane. So here, let's say our epsilon is plus minus 1.5, and we are plotting the scatter plot. And here, this is how it looks like. Okay. So we have explicitly specified 1.5 here. And even if we specify 2, the results are going to be not such a big deal. Okay, because the model at the end of day is this decision boundary. Model at the end of day is this decision boundary, and decision boundary needs to be such that it goes through the center of the data. Okay, all right. Now, SVM regression in scikit-learn with epsilon 0.5, we basically generate the random number, making the relationship, fitting this. Okay, this we have already done. And if the epsilon is zero point 0.5, it's going to look like this. But the model is going to be very similar to the previous one. And for epsilon zero point 0.5, this is how it looks like. Okay. Now we can find the instances of the streets and plotting. This is all okay. So this is how we have. So we are trying to show that these are the instances which are beyond the line, and so on, right? Okay. So let's just take a look at the difference between epsilon zero point 0.5 and 1.5, right? What do you see here? That this is the epsilon 1.5 and this is the epsilon zero point 0.5. These are the instances beyond the vector, these support vectors. These are the two support vectors. So these are the instances there. Okay. So epsilon 1.5 is overfitting. That's right. Okay. Okay. So in simple words, a number of instances of the streets are higher for smaller epsilon, and we really cannot conclude on which is the better model. The goal is to maximize the number of training sets within the epsilon line. Okay. Yes. So epsilon zero point 0.5 needs more tweaking and so on. All right. In simple words, though the size of epsilon is going to, if we increase or decrease epsilon a little bit more or less, this resulting line is going to be not be this won't just suddenly change because we changed epsilon. If you see, this line and this line are kind of very closer. You see, these lines, this is and this are kind of very closer, right? Just that when epsilon is more, the number of instances that are fitting in are more, and epsilon is less, the number of instances are going to be less, right? But we cannot conclude which one is better. The goal is to maximize number of sets within the epsilon line. Okay, so we can just tweak epsilon, try all kinds of values, and see which one is doing good, and and that's the story of entire machine learning, right? Now, there could be the similar case like a linear SVM. Similar to that, we can have nonlinear by having either the kernel trick or by the way of polynomial kernel. Okay, so a kernelized SVM regression model can be used for nonlinear works, right? We could have like nonlinear works in the sense that here, let's say degree is 2, C is 100, and epsilon is 0.5. That's what it is. And right, kernelized SVM regression model can be used. Does epsilon also change the model? All right. A question is, does epsilon also change the model? A little bit, yes. It does change the model a little bit. Okay, but there won't be too drastic change. Okay, you can see here these two data points, you see, these two data points are in the line, right? While here the line is towards the right. All right, so we could actually just take the same analogy, and the way we had a straight street earlier, we just bent it to fit the nonlinear data. If we had nonlinear data like this, we could basically just introduce degree and get the results. So a kernelized SVM regression can be used. C is the penalty of being outside the margin or the error of classification. Higher C, the if the as the C increases, the classification increases, and there will be, okay, let me go back here. So what's happening is that in case of regression, specifically when we have data which is nonlinear, we could have three parameters in case of kernelized SVM regression. First one is degree, second one is C, third one is epsilon. Epsilon is the width of the street which we specify, and C is what kind of violation we have. If the C is higher, we um, we basically don't let go of we let go of many instances. Or you can say that if C is higher, regularization is higher, and the degree is 2 here. Degree meaning the we are using a kernel internally. Kernel in the sense that we are generating new columns hypothetically, and those columns are based on the existing columns by squaring and so on. Okay, so in SVM nonlinear regression, a kernelized SVM regression model can be used. and the C is the penalty of being outside the margin or error in classification, right? C is that penalty. Higher the C, there'll be less violations in case of classification, and there'll be in regression, there'll be less regularization. Okay, so all right, this I thought the other way. If you have higher C, there'll be less violations. Okay, I was thinking it'll be more violations. So if okay, so higher the C, smaller used to be the street, right? Okay, or higher the C, the bigger used to, no, the higher the C, the street was thinner. Correct. Yes, that's why there were lesser violations. And in case of regression, if the street is thinner, there will be lesser regularization. If the street was thin, which is lower, if the street was bigger, like lower C, the in case of classification, there'll be more violations, right? Because lower C means the margin was higher in case of classification, and therefore, if the margin is higher between two classes, then there'll be more violations, right? And in case of regression, there'll be more regularization. That's how you can think of it. Okay, so all right. So basically, all we do is we from the SVM package of sklearn, we import the SVR, and we initialize the SVR with the kernel spoly, and we pass degree C and epsilon to the constructor of SVR. And once we have the object representing SVR, then we call fit on that kernel. Okay, so yes. All right. So basically here, this is how we generally use, instead of using linear SVR, if you want to use the polynomial one specifically for complex data, then we can simply say kernel equals poly, and we can tweak the degree, C, and epsilon in order to get the best results. That's essentially what we that's essentially what we call as grid search or fine-tuning your model. Okay, so nonlinear SVM regression in scikit-learn for a quadratic distributed data looks like this. And by the way, those who are wondering why SVM is so important, SVM has been before the deep learning came into play. SVM has been the front runner of machine learning. The entire world has been using the SVM before that, and people thought that they could solve all kinds of problems. The main problem that happened with SVM is that they required a lot of memory and lot of CPU cycles, because of which the newer models like neural network and so on, or XGBoost, they took the precedence. Okay, so that's why we basically had been using SVM and been learning SVM a bit. Okay, so for smaller data, SVMs are a cool way of getting the results better, and you can't get that kind of results with any other model. Okay, if the data is that small. Okay, so generating random numbers and making quadratic relationship, this is what we did earlier also. Just we generated this kind of data, and then we basically are trying to fit the support vector like that, and then we are plotting the margin lines. So this is how it looks like, and we finding the instances of the street is basically using, we go through the line and check if the predicted value is greater than what it is or lesser than the boundary value. Then we figure out whether what is the color, or what should be the color of the instance, and that's it. All right. Now, let me just walk you through the notebook, though I'm going to just execute each part of it. So we did this part. All right. If you have any doubt right now, so let me just go through each line quickly so that we are all on the same page. So all we are doing here is we are importing random, we are importing the PLT, we are importing the pandas, right? And here we are initializing the seed. We are setting the seed so that the results are predictable. setting the number of instances, then we are generating X. Like this is, I hope everybody is clear what does it generate, right? If you're not clear at any point of time, what you should do is you just, okay, you just try it out, okay? So you could just say rnd.random, and I'll say five rows and one column. Okay, so this is how it looks like. There's only one column. If we say 5 by 4 columns, there are 4 columns and 5 rows. Sorry, yes, 5 rows and 4 columns. So just know this part. So for m number of instances, which is 50 rows and 1 column, we generated x. X is 2-dimensional one. And when we multiply something with 2-dimensional, that we generate the 2-dimensional matrix. And afterwards, we are saying here that add 4 to it, and then we add a random noise, right? When we add the random noise, so uh, what's happening is this won't be a perfect equation. It'll be a little bad equation, and that's why the data looks like this. And when we say unravel, it's going to convert it into single row. In case you're wondering what it means by unravel, just try doing try doing this. Let's say for 5 records, this is how it looks like. And if you say revel, not unravel, if you say revel, this will basically convert it into single row. Okay, I hope it is clear to you. All right, so that's about plotting the data. Let me just move ahead. And here, I was thinking actually, I'll just give you an overview of each line that'll help you in understanding. So this is linear SVR. We initialize the class by passing epsilon a. This is the keyworded parameter. In Python, you can have keyworded parameter, and then we are saying fit. And then there is linear space, as in we are generating these values from 0 to 200 100 such values. If you don't know what does it mean, just try it out right away and so on. Okay, now here we got the intercept when we trained it. When we did fit here, we got the intercept. This is the intercept. Okay, and the model gave us the intercept. Okay, and then we sorry, model gave us the intercept and model gave us the slope. Okay, so this is the coefficient 0 and this is coefficient 1. Okay, so you can think of it mx plus c, right? And you see that we are plotting that on the plotting x and y here. Okay, and what happened to suddenly this? Okay, this one. We are saying plt dot plot, and we get the straight line. Okay, now that's about it. So what we did was we generated new set of x's and new set of y's, and using which we generated this line. Okay, so again here we are increasing y's plus and minus 1. Okay, and using those y's generated by, so we do plus some value minus some value, and we plotted those values in here. Assume library does not give predicted values directly. Okay, SVM library doesn't give predicted value. No, it does give directly. So it okay, you can use predict, of course. You can use predict, and here you can see these are the y predicted for any x values. Okay, all right, good questions. Keep asking these questions. This is good. Now moving ahead, so we are predicting using SVM, and then we can basically use x and y. Okay, so all right, moving ahead. All right, so this part also is the same thing. We are trying to plot it. and trying to plot it. It's pretty much okay. We talked about same thing we are doing here. We basically are plotting it. In this time, we are using SVR with kernel this. Okay, that's all. And we get wonderful results. Okay, so great. So this is the kind of results we get. Moving ahead, so let's just take a look at all kinds of charts. So the same mechanism of plotting the other lines we are using here, and the exactly same mechanism that we used above, just that for different hyperparameters. So you can see clearly that degrees 2, and epsilon is also same. The only thing we have changed is from 100 to zero point zero 0.01. Now you can see that here, here it was not really missing out much values, but here it's missing out many values. Okay, as we decreased C, this is what happened. Okay, smaller C means larger margin and so on. So the if C is higher, I think the regularization is heavier. All right. Yes. So here I think this is better to plot. So if the epsilon goes higher, lesser number of instances of the street, that's very clear. If the C is higher, less number of instances of the street. Okay. So higher C, higher EPS, um, uh, so higher C, less number of instances of the street, and higher epsilon again is the street is going to be little more bigger. You can see the street is bigger, and therefore higher number of instances. Okay, so lesser number of instances of the street. So the idea should be, in case of regression, that epsilon remains small. Epsilon remains small so that we have a street smaller, so that we don't spread out too much, and the C should be a little higher. Okay, so you can see the difference. If the epsilon increases without increasing C, this street has become bigger. That's very clear to all. If the epsilon remains same and we have C as very small, so what happens is it starts missing out many data points. So it has missed out more data points. Okay, all right. So higher C basically means less regularization here. Ideally, it was supposed to have more regularization. That's what I'm wondering. As per my understanding, the higher the C, more the regularization. No, it's actually the other way. In classification, it was the other way. In case of regression, it's less regularization. Higher C, more underfitting. Okay? Higher C means higher bias. Okay, so you are right, Deepak. Thank you. So that actually that's what is happening, and my notation with respect to C was different. So higher the C in this case. Okay, here the thickness of street is not represented by C. Here it's represented by epsilon. And in case of regression, so the meaning of C has entirely changed. So as the as the C goes higher, it has when C goes no, actually, let me just go back here. Okay, higher C, less regularization. Good. Higher the C, less regularization. Yes. Higher the C, higher the C, less regularization, meaning it starts kind of overfitting. You can see. Okay. While lower the C, more is the bias. Okay. Lower the C, more is the bias. Okay. Higher the C, higher overfitting. As in, lesser bias, lesser regularization. Higher the C, lesser regularization. If the C is lower, there is a high amount of regularization, which means there is a huge bias, as in we are leaving out so many data points and so on. Okay, and similarly the case here, and so on. So if you drop the value of C, it'll basically become kind of straight line. If you increase the C, it'll become more nonlinear. Okay, so in both the cases, as you increase C, there will be less number of instances of the street, less number of instances of the street. No, it's not really true. It's not really true. Yeah. So higher the C, yes. So higher the C, as the C is higher this side, there'll be less number of instances of the street. So here, this is the one which has a maximum C and maximum epsilon. There are less number of instances that are going beyond the street. All right. So this is basically the way we look at it. And okay. Also, if you take a look at this one, between this and this, which one will you go for? Yes, first one, right? That's right. And between this and this, first one. Between this and this, between this and this, the left one or right one? Left one, right? So essentially, this is the one which is the best model out of it. Correct. Right? Because this one had just too much bias. It's just behaving like a straight line while it was supposed to behave like a curve. Same is the case here. And also here, since we increased the epsilon, we started absorbing all the data points that may not be necessary, right? And so on. So that's pretty much. However, as the epsilon, okay. And please note that to do the prediction, we always use the decision boundary. You see the middle boundary. Use we do that. We use that for prediction. Okay, we use that for prediction and to give the result. All right. So, however, the if we have higher epsilon and lesser number of violations, does not always imply we are going to have a better model. Similarly, if we have higher C, it can lead to overfitting, and lower C could lead to underfitting. Okay, so higher C means the more overfitting. Similar is the case with higher epsilon. Okay, so what we learned in case of SVM is in case of SVM classification, we learned the linear classification in the beginning, bad model versus good model based on generalization, right? That's where we came up with the idea called large margin classification. In case we have total number of instances really high and we want to do classification, we could use the SGD as well. Okay, we could use the SGD as well, along with, we call this hinge loss. There is a term called hinge loss. Hinge loss basically means exactly the same thing, that we are trying to fit the bigger street between the data. Now the hinge loss is what the SVM SVC provides to us. Okay, so where if our in number of instances are smaller, number of instance is smaller, and we want good model, we can use SVM. If the number of instances are more, but we want this the width between the classification the two classes to be high, meaning we want a good classification, we can actually use SGD with the hinge loss. Okay, so SVM is sensitive to feature scaling. Okay, we learned about hard margin versus soft margin. Then we learned about the we also learned about the nonlinear SVM classification, adding polynomial features, and solving using kernel techniques. Adding similarity features like Gaussian RBF functions and kernel trick, those are the things we learned about the nonlinear SVM classifications. And we also um, they did the computational comparison for SVC, SVC linear, and SGD classification. So we learned that the SVC was having m squared into n being the features, m being the instances, and therefore we concluded that if you have too many instances and your data is non-linear, you should not be using the SVM. If your data is really complex and your number of instances are low, then you can use the SVM. All right. So SVM regression, SVM linear regression using linear SVR and controlling the width and the margin using epsilon. That's what we learned in SVM regression. Using kernelized SVM regression model for model to model the nonlinear models like SVR with kernel and standard scalar. So this is what we learned. As in, what we learned was that we can use the SVM, though SVM were initially designed for classifications, but you can use the same SVM mathematical model for the regression as well. Okay. So if you are planning to learn how does SVM work, I strongly recommend this particular link. Okay. This particular link is quite useful if you are trying to understand maths. In case you get stuck on this, you are not clear about some part, please let me know. All right. I really like this one. It would help you understand. Okay. All right. So this was the part. Okay. So if you want to study a little bit more, how does the SVM work? I'll suggest that link. Okay. Now coming back to it, in case you want to know that, let it. Okay. So all right. So all we are trying to, I can actually explain to you, but okay. All right. All right. I would say that you take a look at the SVM in case you want to go into more detailed problem. Okay, we will learn that part. All right. So basically what we are trying to do say here is this, that the this means that the thickness has to be maximized, and violations should be lesser. This means the violation should be smaller and thickness has to be maximized. These are the two conditions that we try to maximize. That's what we are trying to do. Do you want to go into the details, or do you want to try it first and then come back and then we can have a separate discussion? Yes, feel free to. Okay. Deepak, Nikita, Robert, Satyajit, and Sumit. All right. I would say that try it first. Then whatever I'm saying will make a lot of sense. Yes, you'll have more questions then. All right. But I mean, my suggestion is that if it's if it's not clear mathematically, it's completely okay, because as long as you know how to use it, that should be good enough. And also a general thumb rule to know that all we are doing is finding geometry way of doing things. That what is the way to figure out the biggest distance between the two data points, right? That's the first thing. Second, using all the data points, what is that biggest thickness which we can fit between the two classes such that the violations are minimum, right? So that's what we do geometrically, and this knowledge should be sufficient to understand what it means by SVM. All right. Okay. All right, so we'll just give a quick intro to decision trees, and that way we will wrap up today's session. All right, should we do the introduction to decision trees? Just the overview, like what it means and so on. Okay, all right. Thank you, Deepak, for letting me know. I'll just check. Probably I need to teach machine learning to my operations team. All right. Okay. All right. As a matter of fact, all of my team who is doing who takes care of the operations in other parts, um, yeah, everybody has a it's mandatory to learn AI for managers course for all of them. Okay. So I think that helps them to for in their career. All right. Coming back to it. So, right. So, so far, we learned the kind of mathematical way of doing things. We drew the line, we drew the curve, we drew the margin, and so on. A lot of things so far we learned was related to kind of geometry, right? Though we call it linear algebra and calculus. Whether we were drawing the line, whether we were drawing the margin, basically it was the plain maths, right? And and basically that way of doing things were great for many problem statement. At the same time, the other way, using the if else kind of conditions, using the normal commonsensical way of doing things, that was decision trees. Okay, decision trees was actually a very interesting concept that was something came into play. So we learn about something called decision trees. Decision trees are very versatile machine learning algorithms that can perform classification tasks, regression tasks, and even multi-output tasks. They're very powerful algorithms capable of fitting complex data sets, also used in random forest. So the example of decision trees is basically if we all have our decision trees ready in the mind. Okay, imagine that you have a question that should you accept a particular job offer. Let's say there's a job offer and you want to accept. So your algorithm is going to be if the salary is at least 50,000, if yes, if the commute is within 1 hour, no. The offer offers the free copy, then yes, accept the offer. Otherwise, decline the offer. Okay. So basically, this is the kind of mental map we have of things, and that's essentially the decision trees. So if we have a mental model similarly, we have this mental model ready with 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 the various kinds of data points, then we can just feed that model. We can just feed the new instance to the model, and it'll be able to predict whether accept offer or decline offer, right? Okay, so based on various features here, what are the features we have? Anyone? In this particular decision, what are the three features that we are having? Salary, okay. Distance, okay. Perks, correct. So coffee, distance, and the salary. These are your three features. And based on that, you have prepared your decision tree, correct? Now, preparing this decision tree is the algorithmic part, but understanding how it works once you have this kind of decision tree, how it works is what we're talking about right now. Okay. Also, please note that it's not necessary that you have salary only used once. You could have further. If the salary is greater than 50,000, then you have second note which says, is the salary greater than 20, lesser than 25,000? Yes. Is it working from home? Yes. Then take it. Similarly, if the salary is greater than 50,000, is it Is it the is it far away from sorry, is greater than 50,000 and greater than 50,000, then then do something else. Basically what I'm saying is that on these nodes it might seem like we are using three features, but same features could be at multiple stages, right? Saying that if the salary is uh, between 50 to 60 and the work hours are work days are only 3 days a week, then accept the offer, otherwise decline the offer. Okay, those kind of things. And so there could be many more parameters, and we could create the decision trees out of the parameters, right? So in case of decision trees, things may look like um, I mean, things may look like that the reasoning is linear. If this, then do this, then do that. But it's actually a tabular structure. You can represent the same thing as a table as we are representing in that tree. We could say there's a column called salary, there's a column called commute, there's a column called offer, and we put the values and the answer. The label is here. So the label is here, you see. This is my label, as in the prediction, and this is my what do you say? The features and the decision. All right. So this is how the decision tree looks like. In the decision tree, all we do is given X, given capital X and Y. First, we prepare this tree. Okay, first we prepare the tree, the algorithm, prepare this model. And when we do the prediction, we just walk through this. Okay, if the feature F is between this and that, then do this. If the feature is not between this and that, then do this. If the feature is greater than this, then do this, and so on. So that's how we prepare the descent. We learn how to prepare. There is an algorithm called CART, which helps us preparing these the descent trees. Okay, so we will learn how to work with descent trees. We will train, visualize, and make predictions with descent trees, and then the CART training algorithm will be using. We'll be learning the CART algorithm, and then we learn how to control and regularize the decision trees, and we will be learning how to use the decision trees for regression. Right here it seems like it's a kind of here it seems like it's only for classification, but can be very well used with regression. As a matter of fact, we use decision trees in end-to-end project for the uh, regression, right? And here again, you can see this very clearly that the decision tree is it can be used for both kind of learning. Please keep in mind it can be used for supervised, unsupervised, regression, and classification. Okay, so in case of unsupervised, we can actually use the decision trees for grouping the data and so on. Okay, so we'll see that those parts as well. And decision trees are wonderful things because they can do the nonlinear regression as well. Okay, we learn how decision trees are capable of doing nonlinearity. Okay, so let us just build a decision tree and take a look at how it makes the predictions. We will learn decision tree classifier using scikit-learn on the famous iris dataset, and then we will see how it works. Okay, so let's just walk through this very well, very quickly. In iris dataset, the iris dataset consists of four features, namely petal length, petal width, sepal length, and sepal width. There are three classes named setosa, versicolor, and virginica, right? We all remember this. Sepal length, sepal width, petal width, and the class label setosa, right? So what we do in this case is the everything is going to be numbers. In case of decision trees, everything is going to be numbers, and it is going to be like decimal numbers. And because that's what we learned earlier, that we convert the text into one hot encoding or regular categories. What do you say that either using using one hot encoding or using the numeric values. So we'll be getting this kind of data whereby there are rows, we call them samples, instances, or observations. Then there is labels, label or labels, we call them class label or target. And then there are features called attributes, measurements, or dimensions. Here you can see clearly what it means by features, samples, and patterns. All right. So it might sound very strange that how will we fit our data into this tree? How will we fit this kind of data? Okay, so that's what we're going to learn as part of this. So this iris dataset has these four features and have we are going to use right now only the petal length and petal width. Okay, we'll see the other features later. Other features you can figure out yourself. Okay, so we will follow the following steps to train and visualize our decision trees. We'll load the iris dataset using scikit-learn. Select only the petal length, petal width attributes. Sorry, load the iris dataset using the scikit-learn. Select only the petal length, petal width features. Train our decision tree classifier on iris dataset. Visualize, and then we basically will be showing it. Okay. So here we just loaded the iris in the normal way. And once we have X and Y, we picked only two columns, petal length and petal width. And uh, I'll go into Jupyter Notebook probably next time. For now, let's just walk through quickly so that we see how to use it. Then, right, we'll anyway go through this again. So decision tree classifier, we are creating an instance of decision tree classifier class, and then we are doing the fit. Okay, there is no big deal. We did the same thing with linear SVC. We did the same thing with SGD classifier, and so on. And once we are done, we can do the export. And here notice that we are exporting the whole model. Here we are exporting the model. We are asking it to to prepare the chart for us. Now we can convert the dot file into something. So we have all of this code written in the notebook. There is a command called dot, which lets you convert the dot file into PNG. And this is how we are training and visualizing a decision tree. Okay, we are training and visualizing a decision tree. And you can see that the kind of mental map we had, it has also created the same thing. Notice that there is here we are saying that if petal length is 2.45, if true, then the chances are that it is going to be setosa. If the petal length is greater than this, greater than 2.45, and petal width is lesser than 1.75, then the chances of versicolor is there is equal chance of both versicolor and virginica. So we go further here. Sorry, let me go back. So if petal length is bigger than 2.45, okay, and then we check whether the petal width is lesser than 1.75. If so, if the petal width is less than 1.75, this will be, the class is going to be versicolor. If it is greater than 1.75, the class is going to be virginica. Okay, so basically you can see that it had prepared the similar mental map the way we had prepared. So this is the boundary, this is the boundary, this is the boundary, and so on. Okay, a question from Deepak is, on what basis max depth is decided? Max depth is basically part of the algorithm. We'll talk about this uh, as we go ahead. Okay, so it'll basically the thing is that max depth of the tree. It keeps on going until it consumes everything. If the max depth we leave it as such, it's going to memorize everything, meaning it will basically fit each and everything into the decision trees, each and everything. Okay, so we have forced it here probably to keep only the depth. Okay, so we'll be controlling the depth. Depth is the first thing that we need to control for decision tree. All right, so wonderful. So we just learned that in case we use decision trees, we can convert the same mental model like salary model for you based on the data. So this information it has figured out, these decisions it has figured out based on the data. Based on the data, it has figured out that we can take the decision based on the petal length as 2.45, and similarly, it has taken the decision that we can make more predictions based on the petal width of 1.75. Okay, by comparing with that condition. So just like you did that, in case my salary is lesser than this, we'll take that, we'll do this, otherwise we'll reject the job. So that's the mental model. Dysentery prepares, we prepare the dysentery, this same mental model from the data. So you can see that the learning of machine learning is very much similar to understanding the way the mind works. All right. So great to have all of you in the session. All right. Do not miss the next class. It's going to be very important because dysenteries are really important to understand the concept of machine learning, because dysenteries are very orthogonal to our understanding of machine learning. We have seen the SVM and linear regression. Both were similar in many ways, but dysentery is entirely different. All right. Bye bye. Have a good day.